Alright, so this is the last section from 4.3 Part 2. So this is fundamental theorem of calculus, specifically looking at applications of physical science which have to do with motion, right? Distance, velocity, and acceleration. Alright, so anti-differentiation is used a lot in physics, right? Using to analyze motion of an object when it's moving along a straight path, right? Oftentimes, so this would be like a free-falling object, right? If I drop it's constant because pull of gravity is what's being done to it. The acceleration is constant and is due to the force of gravity, the pull of gravity on the object. As long as I'm near the ground, right, we consider it constant, right? That's that negative 9.8 meters per second squared or negative 32 feet per second squared, depending on which units, but it's constant. The force of gravity, the acceleration due to gravity, is constant. Alright, and so suppose that remember, the derivative of position, that would be the distance or the height the function is at a given time. Its derivative is velocity, how fast it's moving in feet per second, miles per hour, meters per second, and things like that. And then the derivative of velocity is acceleration, right? That's the second derivative of our position function. It'd be meters per second squared, feet per second squared, and miles per hour squared. Alright, well, for our applications in this set, our acceleration will be known and given to us. Alright, either it'll be a function that they'll give us, where acceleration is this, or it'll be constant, considered due to the pull of gravity, which is constant. And they will tell it to you in the application. It'll either be, it's constant and negative 32 feet per second, or negative 9.8 meters per second squared. Alright, based on our acceleration, we can work backwards, right? We can go backwards and find velocity. Alright, give an initial value and all of that. So we still have to, so this is kind of like initial value problems and using the fundamental theorem of calculus or initial values to go backwards and find velocity and then working backwards and finding position, right? But we do have to be given where did we start and how fast was our object moving at the start. Right, and so long as we know what acceleration is, we can work backwards. Right, so velocity would be the antiderivative of acceleration, right? The integration of acceleration gives me velocity. I find the general antiderivative, and then I would have to find this. This would come from the initial value, right? I'd find c using whatever my initial velocity is. Right, and that had to be given to us. Right, c with the initial velocity. It's actually stated there. I didn't have to write it out. Alright, then we could do one more antiderivative, a second antiderivative to find position. Right, the antiderivative of velocity gives me my position. Position would be how far my object has traveled from my initial position, which also could mean the height of the function. Suppose it's launched, right, it'd be the height above the ground. So position, height function. Again, in order to find that constant, they would have to tell us an initial position. Alright, how high were we at the start, usually is what they're given, which is why it's called an initial position. Alright, so we're going to look at specific applications of this, where we're going to work backwards from our derivatives and our second derivative, alright, our acceleration to get us to velocity and our velocity to get us to position. Alright, so our first example. Suppose, now we keep things simple in this class, alright, we neglect a lot of things, but suppose all we're interested in is the pull of gravity, because that's the biggest force at play, right? That's the biggest force at play. Friction and surface stuff are smaller. Alright, so suppose we take a penny and we drop it near the top of the Empire State Building, alright, at a point that is 1,200 feet above the ground. That's its initial position. That's how far above the ground, how high it was when we dropped the penny. Assume a free-falling model applies. A free-falling model means that we're only assuming that the pull of gravity is the only force at play. Right? We're assuming it's happening in a vacuum. There's no wind resistance or friction. Right? It's just the force of gravity, which is constant. Right? If I'm near the earth, near the ground, it's constant at 32 feet per second squared. Right? How long does it take the penny to hit the ground, and what's the speed of the penny at the time of impact? Well, we'll have to use integration to do this. Alright, there's some subtle things that we know. Alright, first of all, I'm dropping the penny, not throwing the penny. Since I'm dropping the penny, alright, when I open my hand, Right? Its velocity, again, in my hand is 0, right? As soon as I open it, then the pull of gravity starts to accelerate it. But the velocity at time 0 is 0. I didn't throw it. Now, it would be different if I took the penny and throw it, and then I'd have to know how fast my hand was moving when I let go of the penny. But I'm not. I'm dropping it, and so the initial velocity is 0. We also know when we drop it, we're 1,250 feet above the ground, so that means my initial position at time 0 is 1,250 feet. Alright, my initial position is given to me. And my acceleration is constant at negative 32 feet per second squared. Alright, that's my acceleration function. So based on that information, I should be able to work backwards and find both the velocity and the position equation, which is what I need in order to answer the question. Alright, so velocity first. Well, velocity is the antiderivative of acceleration. Alright, and so our velocity in this case is the antiderivative of the constant acceleration due to gravity, which is 32. Alright, so my velocity is negative 32 times time plus some constant. But my constant 0, right? When I plug 0 in, I should get 0 out based on my initial position. And so that means this should 0 away. Right, so there is constant of 0. And so this is the velocity equation, right? That will give me the speed of the penny at any time in feet per second. Alright, so there's the velocity equation. Now the position equation. How far is the penny above the ground at any time? That's what the position is. Which again, capital S of x is what's typically used, although you could use h of t if you wanted to. Often h is used as well. Alright, well, the position equation is the antiderivative of velocity, which is our negative 32 times time. So that would be negative 32t squared divided by 2 plus some unknown constant, which is where I'm going to use this to find my unknown constant. Negative 16t squared plus c, but I know at time 0 I'm at 1,250 feet. Well, that's the constant, right? At 0, that's how high I am. And so my initial position, excuse me guys, is that, and so that's my c, right? That's my constant. And so my position equation is negative 16t squared plus 1,250. Alright, and so there's my position. Alright, now I'm going to use them to answer my question. Alright, so the question was, how long does it take the penny to hit the ground, and then what speed is it at that time? Alright, so the how long question is this. How long will it take the penny to hit the ground? Well, it means how long will it take it to travel that 1,250 feet. So we're hitting the ground, position is 0, right? The height of the object is 0 feet from the ground. And so we want to know how long it'll take that position equation to reach 0. Alright, so I take my position function and set it equal to 0 and solve. Alright, so 0 is equal to that negative 16t squared plus 1,250. Alright, that's when it hits the ground, right? It's traveled that 1,250 feet. So I move that 1,250 to the other side. Don't forget t squared, so divide by 16. And that's not a real pretty number, so I'm just going to leave it for right now. I'll round it when I get to the final answer. Alright, so my 1,250 divided by 16. And then it's t squared, so I will have to take the square root of that. And usually we do plus and minus, but time is always positive. Alright, so again, typically we do plus and minus, but I only want the positive. Right, and this is where we'll round. So when we plug that in, square root of 1,250 divided by 16, right, that's all under my square root. Alright, comes out to be about 8.839 seconds, so I'm just going to round to 8.8. Alright, so the penny takes about 8.8 seconds to hit the ground. Alright, so that's the start. So that's how long it takes to hit the ground. Alright, now how fast was it traveling? Well, I use this. This would be how fast is my velocity at the time it hits the ground, well, it took 8.8 seconds to hit the ground, and so we plug that into the velocity equation. So negative 32 times 8.8 seconds. Alright, so 32 times 8.8 seconds, so negative, if it is moving downward, so it should make sense it's negative. Alright, so about negative 281.6 feet per second, right? Because we're in feet and seconds, right? Negative means it's moving downward at that time, and it is, right? It's being dropped. Which is, to put it in context, that's about 190 miles per hour, in case you're curious. Alright, so it takes the penny about, since I rounded, 8.8 seconds to hit the ground, and its speed is 281.6 feet per second, which, like I said, that's roughly about 190 if you convert it. It's right around 190 miles per hour. Again, in reality, will it be going that fast? Probably not, because there'll be some wind resistance and some friction, and so that'll slow it down a little bit. Alright, but this would be, suppose there wasn't any of those things. It was in a vacuum. Alright, it's just simply dropping. Well, it'll take it about 8.8 seconds to drop 1,250 feet, and it should be traveling around 281.6 feet per second. Alright, second example. Suppose that we have a water balloon launcher that's been installed at a tree house. So we're in a tree house that's 30 feet above the ground. Alright, the vertical velocity in feet per second. Alright, so that would be the speed of the water balloon t seconds after it's been launched is given by that equation. And so now we kind of know where these parts come from. The negative 32t, that comes from the acceleration due to gravity. And the 40 would mean that's how fast the balloon is traveling when it's released from the launcher, right? That's its initial velocity. Alright, well, what we want to know, so there's the velocity equation. That's how fast the balloon is traveling at any time after it's been launched. So at time 0, it was traveling at 40 feet per second. Right. A 6-foot tall person is standing on the ground and gets hit by the launched balloon. How fast was the water balloon falling when it hits the person on the top of their head? So we're assuming, again, it's going to go up, come down, and hit the person. Actually, it starts out higher than that. It'll be starting out in a tree house. So it starts out in my tree house, which is 30 feet above the ground. It'll be launched. It comes up. I've got my person on the ground that's 6 feet up. Comes down and hits them on their head. And we want to know how fast it was traveling at that time. Alright, so once it's gone up and come down, how fast was it traveling when it hits the person on the top of their head? Alright, well, we need to know how long it takes to get to that distance. How long does it take to get from being in the tree house, which is 30 feet above the ground, to hitting the person on the top of their head, which they're 6 feet above the ground. So we need to know how long it takes to travel from the tree house, 30 feet above the ground. Alright, this would be 30 feet above the ground to the hitting the person, which they're 6 feet above the ground, right? So we need to know how long it travels to get to that 6 feet above the ground. Right, and then we'll plug it into the velocity equation once we figure that out. So the first question we need to answer is, how long does it take? Alright, what is the time it take to go from the launch, alright, which is in the treehouse, to hit the 6-foot tall person? Right, and again, it's on the top of the head, so how long does it take to go from the treehouse to hitting the person on the top of their head? So 6 feet above the ground. So we need to find the position equation at 6 feet. So I need to find the position equation and then set it equal to 6 feet and find time. Alright, so there's two parts to this. First, I need to find my position equation. Alright, how long does it take to reach a certain height? And then we find specifically how long does it take to reach the height that we're asking for which is 6 feet above the ground. Alright, well, we need our integral function to find our position equation, right? That's the integration of our velocity, which is our given 32 plus 40. Alright, so antiderivative of our velocity finds position, and so antiderivative of the 32t plus 40 is negative 32t squared divided by 2 plus 40t plus some unknown. Alright. So I need to figure out what that constant is. Alright, well, that's why they give us this piece of information. We started at time 0, 30 feet above the ground, right? When it's launched, it starts here, right? This is where it starts. This would be time 0. Alright, so its position at time 0 was 30 feet. Alright, that's its initial position. So that would be the constant, right? At time 0, it's 30 feet above the ground. And so the position equation would be negative 16t squared plus 40t plus 30, right, in feet above the ground. Alright, so there's step 1, get the position equation. Alright, and so that's the part we needed the calculus for. The rest of it's just algebra. I need to know, well, how long it takes it to reach a person that's 6 feet above the ground, right? We want to know how long it takes to hit that person on the side of the head, on top of the head. So how long does it take to go from the treehouse, which is 30 feet above the ground, to hitting a person that's 6 feet tall, so 6 feet above the ground. Alright, so we need to find the time it takes to reach a position of 6 feet. Alright, so I take my position equation, set it equal to 6, and then now I just use algebra to solve for time. There's a few ways you can do it. You can solve it graphically, you can solve it using the quadratic equation, or factoring. This one does factor. If I subtract 6, so using the quadratic equation or factoring, the first step you have to do is set it equal to 0. Alright, so move the 6 over, set it equal to 0 to get negative 16t squared, 40t plus 24. Alright, I'm going to solve it by factoring, but you could use the quadratic formula. You could graph it, find its zeros. Alright, first of all, I can factor out a negative 8 out of each term. I'm going to divide a negative 8 out. So when I divide a negative 8 out of negative 16, I get 2t squared. 40 divided by negative 8 is negative 5. And 24 divided by negative 8 is negative 3. Alright, and then I use the guess check method. Alright, factors. So first of all, 2t squared can split up into 2t times t. Alright, then I know I'm going to have a positive and a negative because of this negative 3. And then I just have to figure out, well, which is it going to be? And so 3 is a prime. The only way I can split 3 up in is the 3 and 1, and one of them's got to be positive and one of them's got to be negative. Well, if I make this negative 3 and I make this positive 1, that's my guess, and then my check is when I take negative 3 times 2, I get negative 6. I add to it positive 1 times t, so negative. Right, my guess is that, and my check is, well, 1 times t gives me t. Negative 3 times t is negative 6t. When I add them up, I get my negative 5t in the middle. Alright, so it checks. Alright, like I said, factoring or quadratic formula would work too. Alright, this gives me a factor t equals negative 1/2. This gives me a factor positive 3. Negative time doesn't make sense, so the only one that works is 3 seconds. So it takes it 3 seconds from when it's launched. Right? So it takes 3 seconds to go from its launch in the treehouse to hitting the person on the top of the head. Alright, so that's how long it takes. Alright, so now we're ready to plug it into the velocity equation. Right? It takes 3 seconds to go from the treehouse to hitting the person on the head. How fast? Well, we now plug that 3 seconds into the velocity equation. Alright, so there's a lot of steps to this. Alright, now we plug 3 into the velocity equation. Alright, so that would be negative 32 times 3 plus 40. Again, it comes out negative 56 feet per second, which is about 38, I believe, miles per hour. Alright, but there's our answer. All right, so when it hits the person on the head, so it takes 3 seconds, so the answer. All right, so it takes 3 seconds from the launch to hit the person on the head. And its velocity is negative 56 feet per second. Negative just means it's moving down, right? It's moving down towards the person, so its speed is 56 feet per second. All right, that one was a toughie. All right, there's a lot of parts that you have to remember, and really the only calc part is the antiderivative, and that's not that hard. The antiderivative, oops, went back too far. All right, the antiderivative is not too hard. A lot of times with these questions, it's the algebra, right? The algebra that's tricky. All right, the only part that's really calculus is this step. All right, the rest of it's just algebra. All right, the last question for this set of notes is problem number 80 in the book. All right, so we've got a particle that's released as part of an experiment. Its speed, 10 minutes after release, is given by this velocity. So again, we're given velocity in kilometers per minute. All right, so it's traveling in kilometers every minute. How far did the particle travel over the first 10 minutes? And how far does it travel over the second 10 minutes? So there's two parts to this. There's how far did it travel from time 0 to time 10. Oops. And then how far does it travel in the second 10 minutes? So answer question A first. All right, so we want to find the distance it traveled, change in position, right? In position from time 0 to time 10, right? So this is the net change, right? Net change in position. So it's position from 10 to 0. Well, that would be integrating from 0 to 10 of my velocity equation. All right, which this one I can solve on the calculator, or you could solve it by hand. Either way is fine. You could find the general antiderivative, plug 10 in, plug 0 in, and find the difference. All right, but I'm going to solve it graphically. All right, so I'm going to graph the velocity. So graph the negative 0.3 t squared plus 9t. I know I need to do 20 minutes, right? Because I have the first 10 and the second 10. So when I go set up my window, I'm going to do a zoom fit from x10 is my minimum, or 0 to 10. Alright, so that would be my min, that would be max, and I do a zoom fit over that. Alright, if you do that, if you graph that function from 0, oh not 10, right, I want to go 20. 0 to 20, right? So again, the edge of my page would be 20. Alright, so it starts here, comes up, and then does look like it comes back down. All right, that would be the edge of your graphing calculator. All right, the first question, though, is asking how far did it travel in the first 10 minutes. And so the first area we want to find would be from 0 to 10. So this is the area that your calculator should shade in. You do your lower value 0, upper value 10, and that area will solve my question. All right, so when I type that out, shade it in, it comes out to a nice number, 350. Alright, so over the first 10 minutes it travels 350 kilometers, right? Our units are kilometers in the first 10 minutes. Alright, so there's the answer to part A. Alright, traveled 350 kilometers in the first 10 minutes. Alright, now I'm ready to answer part B, and again, I'm going to use the calculator, so I'm going to use the same graph. I'll probably regraph it and get rid of this area, so I'll just hit regraph. Alright, so same function, that's still my velocity function. Alright, so I'm not changing anything, I'm just regraphing it so I don't have the area anymore. Alright, so part B is now asking for the second 10 minutes, how far did it travel? Which means from 10 minutes to 20 minutes, right? That's the second 10 minutes. How far did it travel? Well, I'm going to integrate my position equation from the 20 to the 10. It's the net change in position from 10 minutes to 20 minutes. And so integrate from 10 to 20 my velocity equation, which was that negative 0.3 t squared plus 9t. Right, which I already have graphed, right? That's this graph here. Right, but this time my lower value is 10, my upper value is 20, and so this is the area I'm finding. I'm finding this area. Right, that's how much I traveled over the second, how far the particle traveled over the second 10 minutes. And it will be a different answer than the first 10 minutes. It travels at a different time. Alright, so when I type that in, shade that second 10 minutes, comes out to 650. Alright, so it means it traveled 650 kilometers over the time 10 minutes to 20 minutes, or the second 10 minutes. Now, it didn't ask this, but I'm going to sort of add part C. Alright, so there's the answer to part B. It traveled 650 kilometers in the second 10 minutes. It traveled 350 in the first 10 minutes, so it traveled a lot farther in the second 10 minutes. And so my last question, so this wasn't in, this is going to be just kind of an add this last question. How far did the particle travel over the total 20 minutes? And you don't have to regraph it. Right? Over the first 10, it traveled 350 kilometers. Over the second 10, it traveled 650. And so over the total 20 minutes, it traveled 1,000 kilometers. Right? That's how far it traveled altogether. 350 over the first 10, and then 350 over the second 10. Right? Altogether, for the total 20 minutes, it traveled a distance of 1,000 kilometers. Alright, so that finishes up this set of notes. Alright, so finishes up this set of notes relating velocity, acceleration, and position to our integrals. Alright, our indefinite integrals for the first couple of questions, and then our definite integrals for the second set of questions, our fundamental theorem of calculus. Alright, so that finishes up that set of notes.